6.4, Fundamental Theorem of Calculus. We have summarized Fundamental Theorem of Calculus Part 1 and 2 as designated in this book. And the important thing is that you can work with this. Hello. Oh, yeah. And this. Okay? All right. Do we have those in our notes? Those two. Okay. All right. So let's go do some practice problems. So right now, I would like you to evaluate each of the following definite integrals. First one, very straightforward. Let's talk about these others before you dig in. Is there a product rule? Have we talked about a product rule for integrals? For antiderivatives? No, because there is no product rule. She's down in 2 rooms down from you. Yes. There is no product rule. There is no quotient rule. There is no chain rule for integration. So don't try and work product, quotient, and chain the same way we do with derivatives. So when you see something like this, eventually we'll learn other techniques to help us get through this. But right now I cannot take the antiderivative of this in the form of root 2 times t minus 2. So suggestions on what to do on that one. Sorry? Distributed. Yes. All right, I just told you there's no quotient rule. So what can we do here? Do it to a power. I'm not sure how. Sorry, I don't know. Well, thank you for guessing. All right. Any other ideas? I see one term in the denominator. So when there's only one thing in the denominator, what can we do with that fraction? We could divide by it, or we could, and distribute it through. You could. Yeah, that we could do. Is that what you meant? 3? Aha. Yeah, we could do that. Or you could break this up into 3 fractions. Right? Because there's just one thing here. So this could be 2w to the 5th over w to the 2nd, minus w over w to the 2nd, plus 3 over w to the 2nd, and then write them each as a power of w. So you need to do a rewrite here. Either multiply by w to the negative 2, or 3 fractions. You could do long division as well, but nobody is going to choose to do that, I don't think. All right, and then in this one, what is my integrand? What am I taking the antiderivative of? Indeed. Well, what's in front of the deal? I know it's nothing, but usually when nothing is multiplied by 1. Thank you. There is a 1 here. All right, go ahead. Take a few minutes and go through A through D. We wanted to make the official rule, because we've done it enough, the antiderivative of x to the n dx is equal to what? And x to the n plus what? Over what? N plus what? Okay. So that's really the only rule we have so far. That's what you're applying here. Go ahead. We have solutions up now for Part A and Part B that we talked through in class. We're now going to step through Part C. So what we said is this requires a rewrite because there is no quotient rule for integration. So we could rewrite this as 2w to the 5th minus w plus 3 times w squared. Yes, sorry, I'm focusing on my 3 here. Doesn't look like a 3. W to the negative 2, correct? All right, when we distribute this through, we get 2w to the what? 3rd minus w to the negative 1 plus 3w to the negative 2. We have just made it so that we can now use the power rule on all of those. dw from 1 to 2. And now I want to take the antiderivative. I'll leave my 2 in front. The antiderivative of w cubed is? Minus, what's the antiderivative of w to the negative 1? Natural log of w. Right? The derivative of natural log of x is 1 over x, which is x to the negative 1. So the antiderivative of w to the negative 1 is the natural log of w. All right, plus 3w to the what? Negative 1 over negative 1. To be evaluated between 1 and 2. So this is 1/2 2 to the 4th minus the natural log of 2 plus, let's see, minus. It will not work. Think about what you get. You get w to the 0 over 0. So we get division by 0. Will not work. All right, minus 3 times, I'll make it over 2. Are we all okay with that? Because that's w to the negative 1, which is 2 to the negative 1, which is 1/2. So there's that one. Minus, now we're going to plug in our 1. 2 times 1/4 or 1/2 times 1 to the 4th minus the natural log of 1 minus 3 over what? Over 1. All right, calculators, or if you found it with your calculator, give me an answer, please. 8.3069. We're going to trust that. And we would go to 8.306 or 8.306. Okay? All right, and then we have the integral of 1 dr. The antiderivative of 1 is r, to be evaluated between 25 and negative 10. So we plug in the negative 10 first, and the 25 and 6. All right. So, questions on C. All right, I'm moving on. That's the same stuff. We'll come back to this. These are going to be on the video, so if I don't get time to come back to these, I will go back and fill them in. Just more practice problems. What about this one? So, piecewise functions, you have to think a little differently. So, if I ask you to find the area under the curve of f of x from 10 to 22, what am I doing? I'm doing the area under the curve from 10 to 22 of what? Look carefully. Of 6 dx. And the antiderivative of 6 is? 6x. To be evaluated between 10 and 22. So we get 6 times 22 minus 6 times 10. Basically, we're finding the area under a constant, we're finding the area of a rectangle, correct? Okay. All right. How about this one? How would we have to rewrite this one so that we could do it? Negative 2 to 1 of what? 3x squared dx plus the integral from 1 to 3 of 6 dx. Okay, we won't step through those, but we need to understand how to deal with a piecewise function and break it into its pieces. Any questions on where we came up with those? Okay, Sam, you with me? Hang on there. All right. Okay. So, what about absolute value? So, absolute value in all of calculus makes you think twice. You have to do something different with it. You cannot take the derivative of it as it stands. You cannot take the integral of it as it stands. Generally, we have to write it in 2 different ways. Kind of like a piecewise function. So what I have over here is a reminder that one of the definitions of absolute value of x is that absolute value of x equals x if x is greater than or equal to 0. And it equals negative x if x is less than 0. So we can do the same thing here with the absolute value of 3t minus 5. We want to find where that 3t minus 5 equals 0, which is where? Yep, we're going to add our 5. 3t equals 5 divided by 3, divided by 3, and we get t equals 5/3. What is that for the graph of absolute value of 3t minus 5? It is the x-intercept, okay? So, this thing looks like, 5/3. It looks like 3t minus 5, that way. And it looks like the negative of 3t minus 5, that way. No. I keep doing it. I don't know why. Okay, try this again. Negative parentheses, 3t minus 5. Okay? So this means if I want to find the area under the curve from 0 to 3, from 0 to 3 is going to be out here, how do I set up my integral? I would have a definite integral from 0 to where? 0 to 5/3 of what? Plus the area under the curve from? Of 3t minus 5. And then we would calculate each of those. Okay? I'm not at 25 today, right? Okay, you all need to stand up. You are dozing. All right, let's take a pause here. Now we're ready. Let's move on. Okay, so now, we have been dealing with what this book calls Fundamental Theorem of Calculus Part 2, which is just evaluating definite integrals. All right, now we're going to use that Part 1, where we are taking the derivative of a definite integral from some constant to x of some function. Okay, so we saw that the derivative with respect to x of a definite integral from some constant to x of f of t dt was equal to what? It was equal to f of x. Good. All right. So let's sit through this and just see that we believe it again. So our first one is the definite integral from -4 to x of e to the, what does that look like? 2t? 2t times cosine squared of 1 minus 5t dt. And we are asked to differentiate each of these. What does differentiate mean? Take the derivative. So we're asked to find d dx of that. All right, well, first up, how is the taking the antiderivative of that thing looking? Yeah, we're not there yet. So let's make life a little bit easier. Let's call that function f of t, lowercase f of t. And we are taking the antiderivative, -4 to x, of f of t dt. Okay, well that we can do. What is the antiderivative of lowercase f of t? What is it? Capital F of t evaluated between where? -4 and x, which means what? Capital F of x minus capital F of -4. Okay, so that's what the definite integral is. And now we are going to take the derivative of capital F of x minus capital F of -4. All right, well, what is the derivative of capital F? It is lowercase f of x. And be careful before you answer me here. What is the derivative of capital F of -4? Miguel, what do we get?
0.
Why is it 0? We're going to get a constant. This is going to be a constant. When we plug in -4 to some antiderivative function, we're getting a value. And the derivative of a constant is 0, yes? So we get lowercase f of x minus 0, and we get f of x, which is exactly what we have seen in the past. We're just verifying it here. Okay? And if f of t was this function, then what is f of x? This function, but instead of t's, we have x's. Now, no DC. Just that. Now, do you have to go through that long process every time? No, you do not. When you see that you are taking the derivative with respect to x of a definite integral from a to x of some function, then you can just tell me it's going to be this function evaluated at x. Yes?
After the 5, the Theorem x.
Clearly that is an x. Definitely an x. Okay. There are no keys left. They're all x's. Thank you. All right. So we have done it enough times where you do not have to go through that long process. Sometimes it'll help you to go through the process because they get a little trickier. But are we all okay with the derivative of this definite integral ends up being this function at x? Okay? All right. So now let's think about b. B is a little bit different. What looks different on b?
Oh, x squared.
That's x squared instead of x, and it's not at the top, it's at the bottom. Okay, so it's changed it up a little bit. So, I need space. We'll go over here, move into the white. All right, so it was the integral from x squared to what? 1 of t to the 4th plus 1 over what? Plus 1? Okay, thank you. dt. And we are asked to take the derivative of this with respect to x. All right, well, things got a little different here because we no longer have a simple x. We have an x squared. And when we take the derivative of something other than just x, what comes into play? One of the special types of rules. Instead of taking the derivative of sine of x, I'm taking the derivative of sine of x squared. What do I need to remember? Chain rule. I need to remember chain rule. So chain rule is going to come into play. I'm going to do it the long way so we see how it comes into play. So again, we're going to let f of t equal t to the 4th plus 1 over t squared plus 1. And we are going to get, let's see, capital F of t evaluated between what? X squared and 1, which means capital F of 1 minus capital F of x squared. Correct? When we do our fundamental theorem part 2. All right, and now we are asked to take the derivative of that. So what I'm doing now is going to be helpful for that lab that you're working on. Okay, this idea of writing it as f of t to make it easier to see what is happening. Okay? All right. So when I take the derivative of capital F of 1, what do I get? Now we're good at that. It's 0. And now when I take the derivative of negative capital F of x squared, what do I get? Negative. Take the derivative of the outside, leave the inside alone. Little f of x squared, leave the inside alone, times the derivative of the inside, 2x. All right. So that means my answer will be negative this function evaluated at what? X squared. So we get x squared to the 4th plus 1 over x squared to the 2nd plus 1, and all of that times what? 2x. And there's our answer. Okay, so now let's think about how we could have gotten there a shorter way, now that we see these patterns. So the first thing I would have done is I would have rewritten this as the integral from 1 to x squared with a negative out in front. So we still have from a constant to some power of x. And then, when you take the derivative of that, that negative still sits out in front, so this is our second method, seeing if we can shorten the process. It's going to be this function, the negative will sit out in front, this function evaluated here at x squared times the derivative of x squared. So it's f of x squared times the derivative of x squared, which is 2x. Okay, so we get used to seeing these patterns, and when we do that, we can get our answer the same as we did down here. Okay? So, as you do more of these, you'll get better at spotting it and jumping to the answer instead of having to go through the whole process. If you do not see it, then you certainly can go through the whole process. Okay? Questions on what we did here? You'll practice. You'll get it. All right. So, let's try that one. And let's see if we can think our way through this part. Here is our lowercase f of t. We're asked to differentiate again. So, the antiderivative will be capital F, evaluated between what and what? Can anyone see what that is? Does it look like root x?
Yeah.
To 3x? All right, so now we're going to have capital F of what? 3x minus capital F of root x, and we're taking the derivative of that with respect to x. And we get what? Lowercase f of 3x times minus lowercase f of root x times what? 1/2. And now we just plug it in. So we get 3x squared sine of 1 plus 3x squared times 3 minus 1/2 x to the negative 1/2. I'm just pulling out the front. Times what? Root x squared, so that's just what? Better? Just x, thank you. Sine of what? 1 plus x. And there's our answer. I promise you, if you come back to this when you are doing that last page of the lab, it will be helpful. Yes? Because what we're plugging in is root x. Okay? Everybody okay with that? Okay. Now you go practice. Let's see. This video will go up